Hello. So, in the previous lecture, we looked at inviscid flow, where inviscid flow we defined as the flow in which the viscosity or viscous effects can be neglected, and that happens generally when the Reynolds number is large. And then we derived the famous Bernoulli equation by deriving the momentum equations for an incompressible inviscid flow in streamline coordinates. And one of the important points that we derived there was that or we should remember that the Bernoulli equation is valid for incompressible steady inviscid flow along a streamline. Okay. So, what we are going to discuss today is what is called irrotational flow or potential flow, and how this is related to inviscid flow, that we will see now. So, irrotational flow, if you remember when we talked about fluid kinematics, when we derived the relationship for the translation of the fluid, and we developed the relationship for substantial derivative, which is dou v by dou t plus v dot del v. We did that, and then we looked at the deformation of the fluid or the angular deformation of the fluid as well as the rotation of the fluid element. And we derived a relationship which was in the form of omega, and we saw that in the simpler terms, which is half of curl of velocity field or del cross v is what we get as the rotation of the fluid element, or we defined vorticity then, which is basically del cross v or curl of velocity. So, the factor of 2 is taken into account in vorticity. So, when we say that the flow is irrotational, that means the rotation in the fluid is 0, there is no rotation in the fluid. So, that means omega vorticity zeta is 0. Now, just to remind ourselves, when we talk about rotation, it is not the, say if you have a flow field which is a vortex flow field. So, the rotation is not talking about the streamlines which are circular in nature, or there is vortex or recirculation in the flow. What rotation here means, the rotation of the fluid particle itself. So, when can that happen? A fluid particle can rotate if when the flow started, the particle has or would have had some rotation by itself. So, a flow in which when the flow started, the particles, fluid particles, they had rotation when the flow started that time itself. So, it was there was rotation initially present in the fluid. Or when can the rotation start during the flow? It will be because for the particle or for the fluid particle to rotate, you need a torque, and torque will be generated when you have a shear stress, because if you take a fluid particle, the body force will be acting at the center of the particle, or the normal force will also be passing through the center of the particle. When you have a shear force, so when you have a shear force, that is the thing that will give a torque, so that the fluid particle can rotate. And how are the shear stress generated? Shear stresses are generated by the viscous forces. So, generally we have seen enough that it is the viscous effects that is responsible for the generation of shear stresses, and in the previous class we neglected the shear stress term because viscous effects were negligible. So, that means that if we have an inviscid flow, then the shear stresses are going to be 0 unless there is some rotation present initially in the fluid. So, irrotational flow will mean omega is 0, or we can write del cross v or curl of velocity is 0. That is the definition for inviscid flow, and as we just discussed, not for the inviscid flow, but del cross V is equal to 0 for an irrotational flow. As we just discussed that for the fluid particle to rotate, there should be some viscous effect in the fluid, or it should be rotating initially. Now, there is no viscous effect present in an inviscid flow, and if the particles are not rotating when the flow started, then inviscid flow will be irrotational. Okay. So, we derived Bernoulli's equation already for an inviscid flow. Now, we will look at the derivation of Bernoulli's equation for an irrotational flow. So, apart from the normal assumptions or the assumptions that we discussed earlier, we will also have another assumption which is for irrotational flow, that curl of velocity or del cross V is 0. So, the assumptions were that the flow is steady, flow is incompressible, and flow is inviscid or frictionless, and it flows along a streamline. And we will see in a minute that for an irrotational flow, it is not necessary that the fluid flows along a streamline. So, even though we have listed down this assumption here, we will not use in our analysis, and we will consider the motion of a fluid particle in general. So, but we will also consider that the flow is irrotational or del cross V is 0. Now, we will start with Euler's equation in the vector form, and assuming that the gravity act along the negative z direction. So, G will have a minus k component there. Okay. So, this is the acceleration, fluid the flow is steady. So, a local acceleration dou by dou t of V is 0, and we have no viscous term, and there are gravitational and pressure gradient term present. Now, what we will do is we will use a vector identity directly. So, which is that V dot del of V. So, when V dot del is operated on vector V, we can show that half of del of V dot V minus V cross del of V cross del cross V. So, we will use this vector identity directly without deriving it. Okay. So, because the flow is irrotational and del cross V is equal to 0. So, this term goes. So, this term is 0, and what we have is now that V dot del of V, which is this term here, that will be equal to half of del V dot V, and V dot V, when you do it, it will be basically V x square plus V y square plus V z square or u square V square W square, depending on what component do you take. So, that will be half of del of V squared. So, that is basically half of grad V squared, right. So, we can use or we can replace this term in the momentum equation by half of grad of V squared. Okay. So, we will replace this and our equation becomes in this form. Now, what we will do? We will consider, remember when we derived the Bernoulli's equation, we considered that the fluid particle moves along the streamline from point 1 to point 2, and that was a vector d s. Here what we will do? We will consider a displacement, but from any point r to r plus dr. So, from vector r to r plus dr, and we can say this vector dr is equal to dxi plus dyj plus dzk. So, the components of dr in x, y and z directions are dx, dy, dz. Okay. Now, we will take dot product of dr with this equation. So, we can write that rho into half grad of v squared dot dr is equal to minus rho g k unit vector dot dr minus grad p dot dr. Now, we will try to find each of these term or each of the dot product. So, first we can say that because rho and g both of them are scalars, and for vector product we need to find k dot dr. So, k is a unit vector along the z direction, and we have dr is dxi plus dyj plus dzk. So, when you do the dot product, the dot product from the first two terms will be 0, and the only thing you will get non-zero is dz. So, dz k dot k and k dot k is 1, k dot I will be 0 and j dot k is equal to k dot j is equal to 0. So, the first two term will give you 0. Similarly, we can write for grad p. So, grad p is basically I dou by dou x of p plus j dou by dou y of p plus k dou by dou z of p dot dr dxi plus dyj plus dzk. And when you take the dot product, you will get dou p by dou x dx plus dou p by dou y dy plus dou p by dou z dz, because only the corresponding terms. So, I and I terms will give you non-zero. Similarly, the product of j and j terms will give you non-zero value, and k dot k terms. So, you will get the value, and from the definition of this derivative, you will see that this is equal to dp, or the total derivative of p. So, we can write in place of grad of p dot dr is equal to dp. Now, we have solved the two terms, or we did the dot product for the two terms on the right hand side of this equation, and now we need to do the same for the equation on the left hand side. So, as you would guess, what we will get is by doing this for d of v square. So, what we can do is when we write grad of v square dot dr, it will be like what we did for p. So, I dou by dou x of v square plus j dou by dou y of v square plus k dou by dou z of v square dot product with dxi plus dyj plus dzk. And when you take the dot product, you will get dou by dou x of v square dx plus dou by dou y of v square dy plus dou by dou z of v square into dz, and that will be equal to dv squared. So, we can write this as when we substitute this value of grad of v squared dot dr is equal to d of v squared, we can substitute in this equation. So, the equation becomes rho by 2 dv squared is equal to minus rho g dz minus dp, and we can integrate this term and bring everything on one side. So, what we will get is p by rho v squared by 2 plus gz is equal to constant. So, we have again reached the Bernoulli equation, but without using the assumption that the flow happens along the streamline. So, what we did is we took the, or we made an assumption that the flow is irrotational. So, if the flow is irrotational, then Bernoulli's equation is valid for any two arbitrary points, and these points need not be along a streamline. Okay. So, similarly, you could use the same approach to derive Bernoulli's equation for an inviscid flow. What you could have done in place of dr, we could have taken a displacement along ds, and from that we could have derived the Bernoulli equation, but we are not going to do that here. You can see that for yourself. Okay, so, the other thing that we are going to do is define a potential function, but before we define potential function, we will look at what is called stream function, and as you would guess that stream function is related to streamlines. So, the stream function can be defined as, for if we consider a two-dimensional flow, the concept is more useful for two-dimensional flow, and the stream function can be defined as the x component of velocity if we talk about Cartesian coordinates. So, let us just write here explicitly that in Cartesian coordinate the stream function is defined as such that u is equal to dou by dou y of stream function psi, and v or y component of velocity is equal to minus dou by dou x of stream function psi. Okay. So, that is the definition of stream function. Now, we can see that this definition of stream function satisfies the continuity equation directly. So, if we write continuity equation, which is for an incompressible fluid, so the concept comes for a two-dimensional and incompressible flow. So, if you have an incompressible flow, then del dot v is equal to 0 in two dimensions, and you can write dou u by dou x plus dou v by dou y is equal to 0. Now, to check if the stream function satisfies it, we can replace u and v by the definition in terms of stream function and see if we get the right hand side, which is 0. So, we can write this as dou by first term dou by dou x, and u is, we can write in place of u dou by dou y of phi, okay, minus. So, this minus comes because we will now replace for v dou by dou y of minus dou phi of dou x. So, this minus sign comes here, and dou divided by dou y of dou psi by dou x. So, that becomes equal to dou 2 psi by dou x dou y minus dou 2 psi dou x dou y. Okay. So, these two terms, as you can see, they are equal, and what you will get 0. So, that means the by definition stream function satisfies the continuity equation for an incompressible flow. Now, we can define or the variation in stream function, which is basically d psi, this is psi. So, d psi is defined as, we can write from the definition of derivative, that is equal to dou by dou x of phi into dx plus dou by dou y of psi dou y. Sorry, I have been saying this phi sometimes, but it is psi. So, please consider that d psi is equal to dou by dou x of psi dx plus dou by dou y of psi dy. Now, we can replace dou by dou x of psi and dou by dou y of psi with u and v here. So, we will get d of psi is equal to minus v, dou by dou x of psi is minus v. So, that will be minus v dx plus u dy, and if this is equal to 0, that means if there is no change in the stream function, then we will have d of psi is equal to 0. So, that means we can write down this is equal to 0. So, if we do that, then what we will get minus v dx plus u dy is equal to 0, or we can get dy by dx is equal to v by u. And if you remember how we defined a streamline, for a two dimensional flow, streamline is the slope of velocity vectors, and we saw that dy by dx is equal to v by u, where v is the y component of velocity, u is the x component of velocity. So, what we see here is the stream function, this equation d psi is equal to 0 basically represents the equation of a streamline for a two dimensional incompressible flow. So, we now know a bit more about streamline in terms of that we can represent streamlines as the lines of constant value of stream function, because that is what d psi is equal to 0 means, that psi is equal to constant. So, streamlines are basically lines of constant stream function or iso stream function values. Now, there is another another useful relationship we can say we can find here, that if you have an xy plane which is in which the flow is happening, you can have different streamlines, and these streamlines, each streamline will have a stream function value corresponding to it. So, let us say these three streamlines shown here, they have the stream function values of psi 1, psi 2 and psi 3, and we can try to see that what is the flow rate between the two streamlines. Okay. And we will see that the flow rate between two streamlines is constant. We know that the flow cannot cross a streamline, so it cannot pass through this direction. So, flow will be between the streamlines only. Now, we will take one line AB and another line BC and try to calculate the flow rate at through cross section AB and through section BC, and try to find are they same. So, if we take that the dimension normal to this screen is 1. So, that is what we say that flow rate per unit depth. So, the depth which is normal to the screen is 1, and we can find the flow rate across this QAB. Okay. So, the flow rate through this line will be integral from point A to B and flow normal to it, which is u dy. We can write this as v dot dA, and from that you will get u dy into of course 1, which is the depth, and we can integrate it from y1 to y2. So, we will get the flow rate. Now, from the definition of stream function psi, we can replace u with d by dy of psi. You can just write the definition of psi here. So, d by d psi is equal to dx into dou by dou x of psi plus dou psi by dou y dy. Now, u is equal to dou psi over dou y into dy, but as you can see along the line AB, x is constant. So, the dx along the line AB is 0. So, when we look at along line AB, we can write that d psi is equal to dou by dou y of psi into dy. So, we can replace this with d psi itself and d psi, and we can change the limits. So, this will be from y1, at y1 the value of psi is psi 1, and at y2 the value of psi is psi 2, or at A the value is psi 1 and B the value is psi 2. So, we can write this when you integrate it, you will get psi 2 minus psi 1 after substituting the limit. So, the flow through this section A B is equal to psi 2 minus psi 1. Now, we will do the same exercise to find flow through this section B C, again unit depth. So, flow rate across B C is Q B C, and we will have V dot d A, and that will give us V d x. From we will integrate it from x 2 to x 3, okay, and that will give us we can replace V by the definition of V in terms of a stream function. We can replace it with minus dou by dou x of psi into dx. Now, again we can look at B C y is equal to 0. So, this term will be 0 here, and we can replace dou by dou x of psi into dx with d psi. So, we can write this is equal to q b c is equal to minus the value of psi at x 2. So, the value of psi at x 2 is psi 2 and value of psi at x 1 is psi 1 of d psi. So, when we put the limit, we will get q b c or flow rate through B C is psi 2 minus psi 1, that is again equal to q a b. So, that means you take any 2 points between the streamlines, the flow rate between them or the volumetric flow rate between the two streamlines is same. Now, you see here that the distance between the streamlines is small here and this distance between the streamlines is large here. So, that means the cross sectional area between the streamlines is changing. So, if the distance between the streamlines is small, because the flow rate is same, if the distance between the streamlines is small, then the velocity is high here and the velocity is low here. So, we saw that volume flow rate between two streamlines is equal to the difference between the stream function values and it is a constant. So, if you have two streamlines and if we know the stream function values psi 1 and psi 2, then we can directly find the flow rate from here. Okay. It is in 2D plane, or we can say flow rate per unit depth as we see here. So, we already saw that if the streamlines are closer, then the velocity is high, and if the streamlines are far apart, then you will see that the velocity is low. So, generally when you see streamlines plot or the contour plot of streamlines analyzing any CFD results, you might see that when they say or explaining the figure, they say that when the streamlines are placed closer to each other, then the velocity is supposed to be high there, and when the streamlines are far away from each other, then the velocity is relatively lower there. We can also do a similar exercise for cylindrical coordinates and can define the stream function psi in cylindrical coordinates again in 2D. So, it will be in terms of r and theta. So, V r is equal to 1 over r tau by dou theta of psi, and V theta will be minus dou by dou r of psi. So, that will be the definition of stream function in the cylindrical coordinates in r theta plane. Okay. Now, we will define another function which is potential function, and as we will show that the potential function is relevant for irrotational flow only, and because it is defined for an irrotational flow. So, the irrotational flow is also known as potential flow. So, it is defined as V is equal to minus of grad of phi. So, phi is the potential function here, and it is defined in terms of that velocity vector that is equal to minus of grad phi. So, that means the flow happens from higher of phi value to lower phi value, and that is why we have a minus sign there. Okay. So, if we substitute this definition of phi, which is the potential function, in the irrotationality condition. So, if we substitute that del cross V in place of V, if we write minus grad of phi, then we will get minus del cross del phi, and this will give us a 0. So, by definition itself, the potential function satisfies the irrotationality condition. So, the velocity potential is defined for an irrotational flow. So, like stream function, we saw that the stream function, by virtue of its definition, it satisfied the continuity equation. Similarly, the potential function, by virtue of its definition, it satisfies the irrotationality condition. Now, you can write this in terms of component, and you can do it in for 2D or for 3D. So, in rectangular coordinate, when you expand velocity vector, you can write u I plus v j plus w k in terms of its 3 component u, v and w along x, y and z directions, and you can write grad phi. So, minus I dou by dou x of phi plus j dou by dou y of phi plus k dou by dou z of phi. So, if you equate the component respectively, then you will get u is equal to minus dou phi of dou x, v is equal to minus dou by dou y of phi, and w is equal to minus dou by dou z of phi. You can also do the same thing in cylindrical coordinates, and there you will get v r e r plus v theta e theta plus w k. So, the velocity components along radial, angular and axial directions, that will be equal to minus E r dou by dou r of phi plus E theta by r dou by dou theta of phi plus k dou by dou x of phi, and we can again equate the components, respective components. So, V r will be minus dou phi by dou r, V theta will be minus 1 over r dou theta of dou phi, and V x is equal to minus dou by dou x of phi. So, we have the definition of a potential function in cylindrical as well as rectangular coordinates, and if we substitute this in the continuity equation, as we will see now. So, if we take a 2-dimensional incompressible irrotational flow, so if we write down the continuity equation, which is del dot V is equal to 0, del dot of del phi is equal to 0. So, we can write this as del 2 phi is equal to 0, which is a Laplace equation in mathematics, and it is a linear differential equation. So, you can find the solution of this equation easily, analytical solution, and that is the reason there has been lot of interest in solving inviscid or inviscid and irrotational flow, because the solution for such flows is easily possible, because the flow can be represented by the Laplace equation. So, now if we consider a two dimensional incompressible and irrotational flow, and we can write down both. We can write down stream function and the velocity potential. So, here we write the definition of u in terms of stream functions. So, u is equal to dou y of psi and v is equal to minus dou by dou x of psi. By their definition itself, the u and v, they satisfy continuity equation for when we write those in terms of stream function, and we let us, because the flow is irrotational as well. So, we can substitute these definitions in the irrotational T condition, which is basically del cross v is equal to 0, and for a 2D we can write dou by dou x I plus dou by dou y j cross product u I plus v j is equal to 0, and when you do that you will get dou by dou x of u. So, when you relate the first term in the two brackets, you will get 0, and when you write take dou by dou x of v. So, first term you will get I cross j, which is k. The direction of this of course will be k, and you will get dou v by dou x, and then when you relate the second term in the first bracket with the first term in second bracket. So, you will get dou u by dou y j cross I. So, it will give minus k. So, you will get minus dou u by dou y, and again when you do a cross product of the second terms of both the bracket, you will get 0. So, this is your irrotationality condition. Now, you can substitute the values of u and v there, that is basically the k component of omega that we derived, right. So, we can substitute in place of v minus dou by dou x of psi. So, dou by dou x within bracket minus dou by dou x of psi minus dou by dou y of u, and u is dou by dou y of psi. So, again what we get from here is minus dou 2 psi by dou x 2 minus dou 2 psi by dou y 2, or we can multiply it by minus or minus 1. So, you will get this equation dou 2 psi by dou x 2 plus dou 2 psi by dou y 2 is equal to 0, which is a Laplace equation in 2 dimensions. Or you can write in vector form dou 2 or del 2 of psi is equal to 0. Now, we can do a similar exercise by assuming the definition in terms of velocity potential. So, we can write u and v in terms of velocity potential. So, u is equal to minus dou by dou x of phi and v is equal to minus dou by dou y of phi. You might notice the differences between the two definitions here. So, you can see that u is defined as dou by dou y. So, when it is x component of velocity, it is differentiated with respect to y for stream function. For velocity potential, it is differentiated with respect to x. Okay. So, in velocity potential, you will have minus sign for both, whereas in stream function it is minus sign only for v component or y component of velocity. Okay. So, when we substitute this definition of velocity potential, it satisfies rotationality or irrotationality condition by the definition itself, and we will substitute in the continuity equation. So, we will substitute these values in the continuity equation. So, when we do that, continuity equation is basically del u or dou u by dou x plus dou v by dou y is equal to 0 for a 2D incompressible flow. So, we can substitute the value of u minus dou phi by dou x plus y and v we can substitute by minus dou by dou y of phi. Okay. Again we will get a Laplace equation in the term dou 2 phi by dou x 2 plus dou 2 phi by dou y 2 is equal to 0. So, for a 2-dimensional incompressible irrotational flow, both stream function as well as velocity potential, they satisfy the Laplace equation. Okay. Now, if we consider a line of constant phi, which is a isopotential, where phi is the velocity potential, and we can find out its slope. So, for an isopotential line, d phi is equal to 0, and this we can write in terms of dou phi by dou x dx plus dou phi by dou y dy is equal to 0, and we can replace the values. So, dou phi by dou x will be minus u. So, you can write minus u dx. Similarly, this will be minus v dy, and from that we will get the slope dy by dx of isopotential line. So, that is slope of an isopotential line, that will be equal to minus u by v. Now, we can also find that what is the slope of a line which has stream function constant, or slope of a streamline, which we already found, which we already saw that this is equal to v by u. And if you look at these two, the slope m1 and m2 of these two lines, they are, when you multiply minus u by v into v by u, what you get is v and v cancel out, u and u cancel out, and what you get is equal to 1. So, m1 into n2 is equal to minus 1, and those are orthogonal to each other. So, line of constant stream function and constant velocity potential, they are orthogonal to each other. So, if you plot lines of constant stream function and of constant velocity potential, they will be normal to each other. Okay. And by their properties, we can, if we, because we know both of them in terms of velocities. So, if we know one, if we know stream function, we can find out velocity potential. Of course, all this we are talking about for a flow which is incompressible as well as irrotational, because the definition of velocity potential is valid only for an irrotational flow. So, let us look at an example where we have a stream function. So, an irrotational flow field, the stream function is given by psi is equal to x squared minus y squared, and what we need to find is the velocity potential for this flow. So, we can write down the value of u for this. So, u is equal to dou by dou y of psi, and that is also equal to, in terms of velocity potential, minus dou by dou x of phi. And we already know what is psi. So, we can find that dou by dou y of psi will be equal to the when you differentiate this with respect to y, first term differentiation will be 0, because x square is not a function of y, and when you differentiate minus y squared, what you will get is minus 2 y. So, you will get minus dou by dou x of phi is equal to minus 2 y. So, you get dou by dou x of phi is equal to 2 y. Okay. When you integrate it, then you will get, you have to integrate it with respect to x. So, you will get phi is equal to 2 x y plus a function which is independent of x, but can be a function of y. So, you will get phi is equal to 2 x y plus a function of y. Now, you can write the v component of velocity. So, v is equal to minus dou by dou x of psi, and that will be equal to minus in terms of velocity potential minus dou by dou y of phi. So, now when we differentiate dou by dou x of psi, or when you differentiate with respect to x, what you will get is minus 2 x, and minus 2 x is equal to minus dou by dou y of phi. So, dou phi by dou y is equal to 2 x, and when you integrate it with respect to y, you will get phi is equal to 2 x y plus a function which is independent of y, but it can be a function of x. So, if you look at two values of phi that we have got is 2 x y plus a function which may be a function of y, 2 x y plus a function which may be a function of x, and if both needs to be true, then f y and f x, they will be equivalent constant. So, what we get is phi is equal to 2 x y plus a constant. So, that is the value of velocity potential given stream function, and we could find the value of velocity potential. Now, so that is all what we have discussed today. Let us summarize what we discussed. First, we defined that what is an irrotational flow, and irrotational flow is where the rotation of fluid particles is 0, and mathematically we can write that that the curl of velocity or del cross v should be 0, that is the irrotationality condition, and from that irrotationality condition we also derived Bernoulli's equation for an irrotational flow, and a good improvement there or an advantage in this is that in an irrotational flow it is not necessary that we need to apply the Bernoulli's equation along a streamline. You can apply the Bernoulli's equation between any two arbitrary points for an irrotational flow. Now, then we defined velocity potential for which is defined for an irrotational flow, and velocity potential is defined as phi is equal to, or v is equal to minus of grad phi, and we also defined stream function for a two dimensional incompressible flow, where we looked at that u is equal to dou psi by dou y, and v is equal to minus dou psi over dou x, and we saw that both for a two dimensional incompressible irrotational flow, both the stream function psi and velocity potential function phi, they satisfy the Laplace equation. You can see that there are the streamlines or the lines of constant value of a stream function, and the isopotential lines, that is the lines of constant value of velocity potential, they are orthogonal or normal to each other. So, when you want to analyze such problems, you may want to analyze in these two coordinates. Now, remember from here what we also got is that the inviscid and irrotational flow, it can be represented by a linear equation which is Laplace equation. we saw that when we got this value when we got Laplace equation del 2 psi is equal to 0, that satisfies the continuity equation in itself. But apart from that, it is not being shown here, but it can be shown that it also satisfies the Euler's equation. So, that is the governing equation for an inviscid irrotational flow. The Laplace equation del 2 psi is the governing equation for inviscid flow. That is the reason that lot of work has been done on the theory of inviscid flow. Okay, we will stop here. Thank you.